Hello, my name is Michael Avery from Cadence Design Systems. In this short video I'm going to show 3 common errors people make when they first start using SVA because they haven't attended a proper course on SVA. For example, they've just seen magazine articles or looked at the LRM and they've written down what they think is correct, and the results they see surprise them because they don't understand what happened. Shown here are the 3 properties that we'll be discussing, and all of them are using this default clock, which is the neg edge of a signal called CLK. So let's start with the first one here. What we've got is an assertion, and what we're asserting is the sequence A followed by B followed by C is always true, which, like all these examples, is syntactically correct, but it almost certainly does not represent what the coder intended to write. So let's take a look why. If we run a simulation with this property and looked at the signals A, B, C, we'd find out why not. So let's take a look at a simulation and see why doesn't this behave how I'm expecting it to. So the signals referred to in the property are A, B, C. Now the key thing about the property is that we've saying we must always observe at every neg edge of the signal CLK the sequence ABC. So what that means is that sequence must start and continue on every single cycle. So if we were to look at these plotted as transactions here, so this stream that's shown here that I've highlighted, this shows you all the states of all the overlapping properties, and we can expand this out. So I'll just use this button here to expand them all out to show every kind of evaluation of that property that was in parallel with another one, or indeed every evaluation of that property from start to beginning. So what we can see here is that on the first 2 cycles this failed. Okay, so if we line that up with the signals on the neg edge clock here, we see this ABC are all 0. Okay, so let's go back and look at the property a moment. What the property says is I must always have that sequence running. So what that means is at every cycle A must be true. In the second and every subsequent cycle B must be true, and in the third and every subsequent cycle C must be true. That's the only way that sequence can start and continue to run from the beginning of simulation. So that's why we observe that result. Okay, 2 failures there. A goes high here and stays high for a while. B goes high the cycle after and stays high for a while. C goes high the cycle after and stays there for a while. So as long as A, B and C, from this cycle onwards, what we get is multiple overlapping passes. So the evaluation of that property starts every pos edge clock. Has A occurred? If so, it's a pass. If not, it's a fail. So anywhere I go and observe the value of A on a neg edge of clock, this will line up with a failure. So the failure shown there is just like a spike. You can't really see it without me moving the cursor off there. So the lesson to be learned from this then is don't say assert a property and then just define a sequence. Because it's almost certainly not what you want. Probably what the person intended to write may have been something like this. Must have implication in there. That does no longer requires A to be true every cycle if I make that change to that property. Okay, so maybe it's functionally still what I wanted, or maybe it's not. But the point being, don't have assert property then some sequence. We'll now take a look at the next property, and what we have is J implies same cycle K. And we've put this system Verilog operator not in front of it. So not is a system Verilog operator. It's not the same as writing an exclamation mark. So if I actually get an editable file, this is not the same thing as doing this. Not that is a Boolean operator in Verilog. This is a system Verilog operator, and what it does is invert the truth of that property. So basically, anytime that property passes, the not operator makes it a fail, and vice versa. Fairly obvious. Now that again is another example, as all of these are, that's syntactically correct, but it almost certainly doesn't do what you intend it to do. It's really hard to understand what that actually means. So what you have to do is work out the times that J implies K is true, and then invert that in your head. So it's not very readable. The tool will process it just fine. It will do exactly what the LRM says. Let's take a look at this now. So this is a useful thing to know for A implies B properties. So all of these descriptions are functionally, P1 to P4 are functionally equivalent. Okay, they all pass and fail under the same conditions. So when you say A implies B, what to bear in mind is the only circumstance under which that fails is if we have A true but we don't have B true, it passes under all of the other conditions. Which means then, if we say not that A implies B, it means that A being 1 and B being 0 is the only condition under which it passes, because every result gets inverted. Which is the same as having written this. So F5 and F6 are functionally equivalent as well. So if that's a behavior you want, rather than write P5, which is confusing to anyone reading it, then write P6 instead. So if we were to look on a waveform plot, what was really saying with that kind of property, P5, which was of the same form that we were describing, it only passes if A is true and B is not true. Every other time it fails. So this was the property. We're doing not a logical inversion of the result of the property J implies K. Same cycle implication. So this is what we're seeing here. J implies K. So on this cycle, if we look at what the result of that is, we're sampling on the negative clock, remember. When J and K both 0, it's a failure. If we've got J true, that's the left-hand side of implication, and the right-hand side of implication K is not true, that's a pass. So we've got a pass on that cycle, a pass on that cycle. We now make K true as well as J, therefore that's a fail. So there we've seen all combinations of J and K now. Please excuse me, we missed the condition where K was 1 and J was 0, which is where the cursor's at here, that negage. And we can see as expected that fails, just for completeness. The final property we look at is an assertion which says I never see that sequence. Okay, so here I'm stating a sequence that would represent an error condition. So our intent when writing this was, if D ever occurs at any time, then I should never see L occurring after it. Okay, that's what that means. So we've got a delay of between 1 and an infinite number of cycles. So once D has occurred, I should never see an L again. Otherwise, I'm expecting to see that fail. So that seems pretty straightforward. So it's okay, by the way, our first example, we said never do this, because it's almost certainly not what you want, because it's no implication in it, but it's okay if you put not in front of it. Okay, so if you have not in front of it, then you shouldn't use implication in here for the same reasons effectively. Okay, so if you say assert property then a sequence, it needs not in front of it, okay, and no implication. If you say assert property without a not there, you need implication in it. So let's look at the results from these waveforms then for D and L. Where the cursor's at now, we're sampling D, and some number of cycles later, it's not important how many, we sample on this edge L, so it should be no surprise to us, given what our intent was, that an occurrence of L after D results in a failure, and we started evaluation here when D occurred, and we ended when the L occurred there. So that seems, exactly what we described, so why am I mentioning it here as a bad coding style? Well, let's move on in time a bit, and we see that D has occurred here, but there's been no L. So if we highlight L, the signal L, we can see there's no occurrence of L, yet our assertion is still saying failed. And if we go back to the assertion, what we said is only if we see that sequence do we want to indicate a failure. But we haven't seen that sequence, yet we still observe a failure. And the reason for this is because this code was compiled with any version of the language reference manual, which is later than 2005. So if you compile with the LRM for System Verilog 2009 or 2012, it's as if you typed the keyword weak in here by default. So saying nothing is the same as saying weak. Okay, and what that means is this assertion actually fails. As soon as D occurs, that assertion fails. So as soon as we start to see the sequence we've said we shouldn't see, i.e. when D occurs, we get the failure. So it's irrelevant what L's doing actually. So clearly that's not what we intended. So if you don't type, if you put nothing here, then the behavior you get is weak unless you're compiling with System Verilog 2005. If I put strong here, so what I'm saying now is strong means this sequence must complete. So in order for the assertion to fail, I must observe D followed by L, not just D by itself. So just putting strong there has changed its behavior now. So that's why we say be careful with this. You have to be really careful with a not operator, what's happening with strong and weak. And it's not even consistent throughout the versions of the language reference manual. It all depends on what version you're using and many other things as well. There's also a Tcl variable. So in the Cadence simulator, and most simulators would have this, there's a Tcl variable whose name is this. If I uncomment that now. Set assert report incomplete. So what that's saying is if it treats everything as being strong by default instead of weak by default if you make that a 1. Okay, so that's why it's commented out. So this is all getting away from the language now and into what tools do specifically. So let's run again then and see what happens. Difference in this waveform if I go and edit this. So what I'll do, resave that. I've saved that, yeah, and I'll just reinvoke the simulation. So basically this does everything it takes to compile and get everything back where I am now. Okay, so let's go and find these occurrences of, you notice now this property which was failing here, though this one still fails of course, D followed by L, but this occurrence of D no longer causes the assertion to fail. Okay, so we've changed the behavior there. Okay, so let's summarize what we've said about why these are bad coding styles. So a quick summary. So this, don't write an assertion about a sequence must always be continuing, because you get behavior you don't expect. Don't put not and a property with implication in it, because it becomes very hard to work out in your head what's happening. If you're saying not a sequence, if the sequence is one like this, like infinite length in there, you have to be very careful about whether you consider it strong or weak. And if you, another point that we haven't shown a property specifically to show it, but if you're using not operator, only have a sequence in here, not some implication. So it would be a bad idea. Although, again, it's syntactically correct. It's a bad idea to put something like this. Let's use next cycle. Because again, it's the same reason there's this one here. It becomes hard to understand what that really means. Okay, so that concludes this then. Hopefully you've learned something, found it useful, and thanks for listening.